Hello, everybody. Good to see you all again. What day of the week is it? I guess it must be Wednesday. Happy Wednesday to everybody. Wow, that's the middle of the week. Math likes symmetry, and in some sense, to me, this is the midpoint of a symmetric week. So that just came to my mind. Well, I'd like to welcome everyone for coming and for chatting about math on this late afternoon. Now, as you know, if you've been here before, this is going to range across a lot of different topics in mathematics and science and goodness knows what else. If you're new here, I want to welcome you to what will not sound like a normal math class. And that's because you probably already took your math class today with your teacher. Instead, what this is it's a chance to talk about all kinds of different topics, which are all united by math. Usually the math is around the level of Algebra 1 or geometry, but the questions we try to answer with it can range all over the place. And what makes us very different from a normal math class is that you drive the conversation. So what I will talk about today is whatever you guys are interested in. And I'll sort of improvise a mini lesson about math using whatever I see inside the chat. So let's go ahead and get started. What do we see today? Oh, there's a question. What color is the shirt is a good question. Well, to be perfectly honest, the shirt is sort of like, it's a very light color of blue, I guess. And that seems to come across as white because of the way the light is reflecting. But let's see, what else can we see here? Oh, this is an interesting question. Somebody wants to maybe have me talk about Conway's Game of Life, and in honor of John Conway, who just passed away from COVID-19. Yes, I'd be happy to talk a little bit about this. Let me see how much I can remember about it. So now, first of all, John Conway is a very, very famous mathematician. He's a very creative person who was able to think of many interesting ways to visualize symmetries. In fact, one of the things he's most known for is analyzing something called a group. These groups are used to study symmetries, or different ways that things can be symmetric with each other. Now that's a very vague definition, but somehow group theory is something that you learn in college. But now this game of life, he was a creative guy too, and so in this game of life, what happens is you imagine that you have a very, very simple set of rules, and that simple set of rules turns out to be able to make lots of interesting things happen. So for example, let's pretend that life just lives on a square grid. Let's just say a square grid. And so if I have a square grid, what happens here? So I'm going to try to draw a square grid. And inside a square grid, oh, that's not the most efficient way to draw a square grid. Drawing a lot of squares will take forever. Instead, this is the right way. So I'm going to draw this big square grid. And actually, in Conway's Game of Life, the grid can be very, very big. But here I'm just going to draw it in a small way. And what you do is at the beginning, you say that some of these cells, some of these locations have things that are alive. Maybe green stands for alive. So there might be some things. Maybe there's something here, maybe there's something here, maybe there's something here. I'm just saying that there's some stuff scattered all about. Okay, some stuff scattered all about. Now the rules of the game of life are like this. So this is what the whole system looks like right now. Somebody said it's too quiet. If it's too quiet, I guess turning your volume up might help. Let me also check my microphone to see what we're at right now. Actually, our microphone looks like it's the same way that it usually is, so I would recommend you turn up the volume. Okay, great. So now the situation is this is what the world looks like at some moment. But then you want to know what will the world look like in the next moment. In the next moment, the way you do this is you look at every single square. And every square looks at how many squares around it are alive. Now, the rule is something like if there are... So just a second. So everything which already has a life... Okay, so this is complicated. There's some set of rules here, which is like if you are already alive, under what conditions do you stay alive? Well, if there are too few people around you, then you die. And in fact, let's see, so how does this work? Actually, if any of you are on the chat, maybe you can also type this in and we'll talk about this. So the idea is that somehow this cell here is unfortunately very lonely. There's only one neighbor. And so the way this works is that if there's only one neighbor, then it's not going to survive. And so in the next round, this one's going to disappear. Similarly, this one only has one neighbor too, so it'll also disappear. Actually, this is a very boring setup because a lot of these are going to die because all of these are too lonely. So the point is, if there is a cell, I call this a cell, but if there's something which is alive, if there's one or fewer neighbors around it, it dies. Actually, there's also another way that things can die. Things can die if there's too much stuff around you. Then you get kind of squeezed out by overpopulation. And so the way that works is that if there are 4 or more neighbors around it, then it dies by overpopulation. So if you filled up the whole thing saying, here's a sure way to make everyone survive, unfortunately almost everyone would die. Because the rule is if you have at least 4 neighbors around you who are alive, then you also die. So far this looks pretty bad. It looks like everything is going to die. And indeed, everyone that's here is going to die. But there is another thing that can cause things to be born. Things can be born if there are exactly 3 neighbors around them that are alive. So let's look at what happened. So if we've got this kind of a situation, all of these will die in the next round because unfortunately they have too few things around them. But in the next round, some things will be born. Some of these squares have exactly 3 neighbors around them. And we count neighbors in terms of diagonals also. So for example, this square right here, this one has 3 around it. I'm going to use a different color to represent what's happening in the next round. So this one's going to appear in the next round because it had 3 neighbors around it which were alive. This one is also going to appear in the next round because it had 3 neighbors which were alive. This one's also going to appear because it had 3 neighbors which were alive. And there are no other things that had exactly 3 neighbors which were alive. And so the situation is every one that was there before unfortunately had 1 or fewer neighbors around it, so it didn't survive. So then unfortunately those disappeared. And this is what it looks like at the second stage. Well, what happens at the third stage? Now at the third stage what happens is anyone who has only 1 neighbor around them is going to die. So that one's going to die because it only has 1 neighbor around it. This one's going to die because it has only 1 neighbor around it. Uh-oh, this is not very good, but look what's going to happen. So both of these will die. On the other hand, this one's okay because this one has more than 1 neighbor around it, and it also doesn't have too many. It doesn't have more than 4. On the other hand, is anyone going to be born? This is going to be pretty interesting. The question was about John Conway's Game of Life in honor of John Conway, who was an amazing mathematician. So now there's going to be some things that are going to be born, by the way. This square right here has 3 neighbors around it that are alive. So that square is going to be born. And also up here too, this has 3 neighbors around it. And already SNF says it will cycle. So this is interesting, right? Like these 2 yellow things will be born because each of them has exactly 3, each of these squares has exactly 3 nearby which are alive. But meanwhile, those 2 will die because they only had 1 nearby which was alive. And so it looks like this. And you know, it's got different colors. I'm just going to make this one also the same color. That is one that survived throughout. Oh my gosh, look what happens. So the next thing that's going to happen is, okay, that one's going to die because it has only 1 neighbor. That one's going to die because it has only 1 neighbor. But look, now it's a loop. I love math. Hey, so do I love math too. Okay, and over here, these 2 will come to life because each of these had exactly 3 around. And so the next thing you see looks like this. And now you already see this is pretty interesting. So it's boop, 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 boop. And in fact, there are these kinds of game of life simulators where you can kind of just like draw a bunch of things around the screen and then say go. And then you watch all sorts of weird stuff starts to happen. Tiger Lee says this is a blinker, right? This is basically showing how a very, very, very simple set of rules can make the thing look like it's some kind of an animal doing interesting things. There are even things called gliders. Somebody said glider. I actually don't remember off the top of my head how to make a glider, but it's possible to make an object that kind of just starts going across in a diagonal direction, just like this, by just putting the right cells on the board to be alive. And then if you just follow the rules, at the next moment, it's 1 down that way, and then it's 1 down that way, and it's 1 down that way, and it just keeps going. U-shape is an exploder. Is that true? Let's find out. So somebody said U-shape is an exploder. Let's try. So now the problem is I don't exactly know what you mean by U-shape, but I'm just going to go mess around with some stuff. And I'll say, look, what if we made a U-shape like this? Just to show what might happen. Now this is a situation which, let's see what happens. So if I made this this is a U-shape. I'm not sure if that's what you meant by a U-shape, but I'll just do it and see what happens. First of all, who's going to die? So the one up here is going to die, and the one over there is going to die because each of them has only 1 neighbor who's alive. Now, on the other hand, so those 2 are both going to go away. Let's see who's going to be born. Everyone else, by the way, is going to be fine because everyone else... No, that one's not fine. This one has 4 neighbors. Actually, I'm trying to remember. The game of life is, like, if there are 4 neighbors, it's too many, right? So this one's going to die too. So this one's going to die, and those 2 up there are going to die. Now the question is who's going to be born. So, oh no, why are we talking about this death at this time? It's probably not a great idea. But then what's going to be born is over here. That one's next to 3. That one's next to 3. This one's next to 3. Anyone else next to 3? Not that I can tell. So this one's going to be born. Oops. This one's going to be born. This one's going to be born, and this one's going to be born. Right? Those 3 are going to be born, but at the same time, some things are going to die. The things that will die are those 2 because they were too lonely, and this one because it was overcrowded. And so now I have this picture. Okay? And you can just keep going. So if you keep going, let's see what will happen. So who's going to survive? Who's going to die? Well, the ones that are going to die, well, this one has 2 already. This one has 2 around it. That's okay. This one has 2 around it. That's okay. This one has 3 around it. It's going to survive. This one has 2 around it. It'll survive. So by symmetry, all of these will survive. And then as all of these survive, yeah, it's a V. We made a V. Now, as all of these are going to survive, now let's find out who's going to be born. And this is where you see that if too many things are born, it's also dangerous because then they start to cause overcrowding. But let's see. So who's going to be born? This one over here is going to be born because it has 3 nearby. By symmetry, that one also has 3 nearby. Oh, just to make it clear, I'm going to turn everything yellow that was there before so that we don't get confused about what we're comparing against. You see, what we're comparing against is which squares which are empty have exactly 3 yellow squares next to them, right? So who else has exactly 3 yellow squares next to them? Looks to me like that's about it. If I'm just staring at this, I don't see anything else that has exactly 3 squares next to it, right? So then the next thing we do is the next round, what we're going to have is we're going to have all of these the same color because those are all here and all alive at the same time. And then you can imagine this going on and on. So who's going to die? Some people have too many next to them. Is that true? This has too many next to it. This has too many next to it. So both of these will go away, right? Both of those will go away, but everyone else is going to stay there. And then how many places have 3? How many people have 3 exactly next to them? So if I look at this, I see these 2 have 3. So I'd be able to have something born here and something born here. I don't actually see anything else with exactly 3 nearby. And if there's nothing else with exactly 3 nearby, then we'll say this one had too many, that one had too many. And you get the idea. So it's making all of these different things bottom, you said. This one, bottom. Oh, well, we wouldn't add another one yet at this time. But basically, we have this thing right now. That one's going to stay there. And if we were to color them all the same color, we have stuff like this. Okay, I'm not going to actually keep going with this because, as you can see, this is best suited for a computer. And if you go on internet and look for these things of like these like game of life interesting things, it's really, really fun. And you can just kind of draw your own pattern and you can see. Okay, so this is showing the game of life, and the whole point of this was not just to have some silly game, but it was to show that some of the most simple rules in the world can turn into something that, if you look at it from far away, looks like it's alive. And I think that was interesting to mathematicians, but it's also interesting, that concept is interesting to people who think about biology, of how in the world could you have a bunch of atoms moving around in the universe and see some kind of life. Okay, so that's all I'll hit about the game of life for today. Let's see what else can we do. I see Pi has a question. Can you explain scientific notation, please? Yes, I can. So, did you know that the Earth is like about 4,000 miles in radius? See, that's pretty useful to call it about 4,000 miles. Is it really, really that important to know exactly how many miles it is, if it's 396 whatever? Well, 4,000 is close enough. Did you know that the United States national debt, how much money the United States owes other people, I guess, or other countries, is something like $20 trillion? I made that up. I'm actually not sure how much it is, but I think it's around $20 trillion. Maybe somebody can actually look this up for me. But the exact number is not super interesting. In fact, I used to live in New York City a long time ago. And when I lived in New York City, I often walked past somewhere in Times Square where there was the national debt clock. And it would actually tell you how much money did the United States owe. And it would just keep ticking up and you'd get very scared as you saw all of these digits. Wow, so I got this 20 trillion about right. Thank you very much to the Christmas Warrior 3847. Yes, we owe a lot of money. But now you see, the point is what's most important about this 20 trillion, and the 22.7 trillion is correct. But what's more important is to know, is it about 20 trillion? Or is it about 500 trillion, right? Like what sort of order of magnitude are we talking about? Or is it that we just owe everyone $100? You know, like we just want to know roughly where is this number. So that's the general idea of scientific notation. The general idea of scientific notation is, in the very simplest version, I would just say 20 trillion. And 20 trillion is 2 times, what's a trillion? Well, a billion is 9 zeros, so a trillion is 12 zeros. So this is 2 times 10 to the 13. Wait, let me get that straight. A billion is 9 zeros, a trillion is 12 zeros, and so 20 trillion is 13 zeros. That's a lot of money, okay? But so this is a number, and you can say that's a number. This is the amount of money that the United States owes. Here's another number, 4,000. 4 times 10 cubed, and that's the radius of the Earth. But this is a way of showing, like, roughly what is the order of magnitude. That's how much 10 there is, how many 10s are multiplied together. And you know, what's the leading digit? Meaning, is it 4,000 miles or is it 9,000 miles in radius? And this thing, is it $20 trillion or $40 trillion, right? But scientific notation lets you do things a bit more precise than that. For example, I saw somebody say 22 trillion, or maybe they said 22.7 trillion. That's giving you more what we call significant figures, in the sense that it's telling you a few more digits. But you see, if I already knew that it was 20 trillion, which is 2 times 10 to the 13, well, in reality, it's more like this, 2.3 times 10 to the 13. And so what this looks like is it's saying, we're being a bit more precise. We're saying it's not just 2 times 10 to the 13. I could give you another significant figure. I can give you one more digit. Oh, somebody said it's 24. Okay, let's use 24. To be perfectly honest, this is already showing you how I'm thinking about the digit. That's the second one after the decimal point. It's not as important. You see, this 2 is far more important than this 4. If I had 2.2 times 10 to the 13, or 2.4 times 10 to the 13, if I'm looking at ratios or like percent errors, that's not that big. Of course, if you think about what it really is in terms of actual money, that's a difference of like $1 trillion or $2 trillion. Feels like a lot. But in any case, I'm just showing that the scientific notation, the purpose of it, is that you will find out roughly what power of 10 it is. Is it 1 million? Is it 10 million? Is it 100 million? And you'll also find out like about how many of those millions or about how many of those 100 millions it is. And that's the principle of scientific notation. Whenever I'm doing a calculation, I'm often thinking in terms of this first most significant digit and the power of 10. And between those two, you can do a lot of estimation. Okay, what else can we get? What other questions do we have here? Oh, wow. So some people here are interested in the app that I'm building. So some of you know that I'm building an app called Novid, which is trying to help stop COVID. It's COVID-19. We're trying to help everyone know whether there's a COVID-19 infection that's close enough to be possibly making them need to behave a bit more carefully. And if you're curious, you can go to our Fri Ap's website, novid.org, to take a look. N-O-V-I-D. Now, the question was, will there be competition from Apple and Google? Well, you see, I don't know if the word competition is the right way to call this. I would like to think that if there's a huge global health problem, I would like to think that the best thing we can do as a human society is to not just say, let's let one group try to figure this all out while we all sit and hope that they figure it out. I don't think that's called competition, to be trying to say, we shouldn't only have one group that we trust in this whole world to try to solve a major problem that affects everyone in the world. We actually should probably have a bunch of different people all trying to be as creative as they can to try to solve this problem. Because otherwise, exactly as No Name said, how can we put all our eggs in one basket? Actually, in my opinion, that would be a very, very bad decision. So I hope that we're actually not going to put all our eggs in one basket. And in fact, the reason why I jumped into action when I got this idea of making Novid, the reason I jumped into action was I said, well, let's at least get another basket and I'll make a basket. And, you know, if it turns out that it's the basket that I made that helps a lot, great, I'm happy. If it turns out that someone else's basket did it, great, I'm happy. But I think that it's extremely, extremely dangerous to go and say, oh, someone else has the problem figured out. Let's let them figure it out. I'm very much of the opinion that if there's a major, major problem that needs to be solved, actually we should go and try to solve the problem. And eventually, if we find out that some other group really, really has a much better way of solving the problem, yes, then you stop doing what you're doing. But until we see that point, it is not wise to go and say they'll probably figure it out. And actually, when it comes to like what Novit is doing, how we're using ultrasonic tech, it's pretty interesting. I mean, I gave a talk about this at the to the Math for America audience. If you're curious at all, there's a video about this. If you just look on our YouTube channel, you'll see a roughly 2-hour talk I gave to like about 200 teachers from New York State. So if you're curious, it's inside there. Right. So basically, the idea is that I think it's great, by the way. When I see what Google and Apple are doing, I think it's great because I think that what they're doing will make it easier for any other apps to do more. And in the end, I think it's very important that we have a bunch of different solutions. There's something else I should also add, which is that it is true that Google and Apple will have theirs out soon, where soon is something not yet defined. We actually have no idea how soon is. Whereas what we've done with Novit is it's available now. And now and soon are very different matters. So what we're trying to do is try to make the now available to as many people as possible. Okay. Whoa. So here's a very interesting question. I don't even know the whole question yet. Let's see what this says. What happens if you take an iron bar and bend it all the way around the Earth? Gravity is pulling at it from all directions. So will it hover in midair? This is a pretty interesting question. I want to figure this out, okay? So somebody says they have done an amazing structural innovation. The structural innovation is like this. Here's the Earth. It's a nice blue sphere, or oblate spheroid, as some people say. And then what somebody has chosen to do is they have managed to make a huge iron ring. And this huge iron ring is just like going around the Earth. But it's just a huge iron ring. And, it's like symmetric, perfectly symmetric, just around the Earth. Then the question is, what will happen to that iron ring? Will it just float in midair? Well, what do you think? I mean, I'm looking at this right now, and I'm imagining, suppose we did this amazing feat of engineering, and we have this wonderful iron ring, and it's going around the Earth. And it happens to be, I'm going to make it simple, it happens to be right around the equator. The equator is going to be important. That is a big iron ring. It's very heavy, very, very heavy. Some people want to make the ring. I'm not sure who will make the ring. Some people are saying tidal forces will break it. Let's pretend there was no moon, okay? So let's pretend we have no moon. These people are just asking, we made this huge bar. Oh, Temp ID says it looks like Saturn. Well, there's a slight difference, by the way. In Saturn, it's not that it's one solid ring, right? You guys maybe know this. Saturn is a ring made of a lot of particles and rocks and dust. So it's not one solid ring. And in fact, that the rings of Saturn are orbiting around Saturn. And it's because they're orbiting that they stay up there. But the question here is, it's just a solid ring. So if I'm looking at this, I'm going to say, okay, suppose it falls down. What direction is down? Does that mean it's going to do this? No, that's not down. I mean, somehow there is a sun. The sun's very far away, but down, it does not mean this way. It is not going to fall down off the Earth like a hula hoop. So that's not going to happen. In that case, what other direction could it go in? I mean, it seems to me quite reasonable. I mean, it seems to me that it probably would actually just stay there. So now the point is that somehow, I see that somebody has made a comment which says infinite dependence on initial conditions, says it falls down at some point. So I think, yeah, Ron Yoder, you have a very good point. It's like, how could you make it perfect, right? If it wasn't actually perfect, then maybe one of the directions would have a little bit more gravity pulling on it, and it might fall into the wrong way. But actually, if I'm looking at this, so I'm actually quite curious. So I'm not actually a physicist, but the way I'm telling you how I would analyze something like this is that I have a sphere, which is called the Earth, and I also have this ring here. And the ring is going to be attracted, the center of mass of the ring is going to be attracted to the center of mass of the sphere. And so it seems actually to me that it would actually hover. So again, I could be wrong, but the way I'm analyzing this is somehow the ring has a center of mass. And that center of mass should be attracted towards the center of mass of the sphere, it seems. But maybe that's not accurate when the things are too big, close to each other. That might be the case. I would have to be a little bit more careful on this. But my gut feeling is that somehow if you actually made it perfect, it would actually just float there. But then the problem is, actually making a ring like that would be quite hard. And also the amount of force which is drawing the ring down, trying to pull it down towards the Earth, is also quite a lot. Ah, yes, Elaine Cho is right. The sun would indeed pull it towards the sun, but it seems to me that it's so far away from the sun right now that it would be more affected by the Earth, is my gut. But yeah, the Earth is not a perfect sphere. That is also true. However, the part that is spinning around, if I put it around the equator, it's probably pretty circular. So I think I don't actually know the answer to this question. I'm quite curious. Yeah, I'm quite curious what's the right way to think about this question, because of the fact that, a lot of times when we think about physics, what we do is we actually will say we can model that circle by the center of mass of the circle, and that the center of mass of the circle is going to be attracted towards the center of mass of other objects. So yeah, this is kind of interesting to me. So yeah, this is quite interesting to me. I actually have to go and dig a lot more into this and try to see. The reason is because my gut feeling, by the way, is that even if it wasn't perfect, if the center of mass moving towards center of mass is correct, then indeed, actually, even if it started off kind of offset, it would actually go into a position where the center of mass of that ring approached the center of mass of the sphere. I mean, maybe some of you have seen these kinds of things before. Oh, the moon would crash into it. Well, yeah. So you see, No Name is talking about perfect symmetry, but I think here's what I want to say. Maybe some of you have seen things like this before. There's like these fun, like physical toys where it's like a tightrope walker, and so there's this rope or this very, very skinny thing going across here, and then there's like a thing that balances on top. It's supposed to look like a person, but it looks sort of like this. And then this thing has like two very heavy things like this. Has anyone seen these kinds of toys before? It's like somehow it's coming all the way down here. And the reason why it balances well, even though there's a very, very small thing which is holding it there, is because somehow the center of mass of this whole object is down here. And so the center of mass is actually below. So yeah, so something about this ring is quite interesting to me. People ask, would the moon exert pressure on it? Yes, it would. But the thing that I'm now quite curious about is, like, even though the moon's exerting pressure on it, if I can treat the whole ring as one object, I'm actually quite curious how that works, because like the center of mass of that object, in theory, should try to move towards the center of mass of whatever is the heaviest object that's around. I mean, if there's a very, very heavy object that's around, which would be the Earth. Okay, so I'll say this is a really great question. In fact, I'm now curious, and I want to go and think about it some more. Okay, what else do we have here? Wow. Looking at all of these different things. So I saw somebody asked, I see. So somebody asked, what's the probability of themselves getting coronavirus? This is Carbon News. So if you want to know what's the probability of yourself getting coronavirus, I think that it depends on what country you live in. In fact, the way that I would initially estimate this, if I just wanted to make any old estimate, is I would say the probability would be based on, the probability would be based on whether or not that country is looking like it's going to spike up. If you are going to have a country which has the coronavirus spike up so that it's not controlled, then unfortunately, based on this R0 infectability rate, the R0 contagion rate of somewhere between 2 and 3, then I'd estimate that probability is probably going to go towards, it's going to go towards around like 50 or 60%. So unfortunately, if the country has a runaway surge of this, then it would be like 50 or 60%. On the other hand, if it's controlled, well, Philip Neller, you say probably everyone will get it eventually. That's actually not completely clear. The reason that's not completely clear is it depends on whether or not we control the whole situation well enough until there's a vaccine. And if there's a vaccine, then you don't get it. Tiger Lee says if you live in Antarctica, you won't get it. That may be the case. I'm not really sure that that's a good reason to move to Antarctica, though. There might be other problems with living in Antarctica. But so my hope is that, we don't actually hit this 50%. I hope that it doesn't run away. Run away, by the way, would also mean that you have millions and millions of people who die. So the hope is that we combine basically some of these stay-in-place measures, so you don't infect too many other people, together with effective contact tracing. That's why we built Novid. And if we do this for long enough, until we get the vaccine, then hopefully your chance of getting it is more like in the, 1% range, 1% to 10% range. That would be the hope. Go to Pluto is another option, but then again, if you go to Pluto, how do you know that Pluto doesn't have even more strange problems that you might run into? Maybe it won't be viruses, it might be radiation. You don't know. Okay, build a moon base and go there. You guys are very, very creative. What else can I do here? Oh, this is a neat question. Somebody asked, Neo Shu asked, why is a four-leaf clover so hard to find? My gut feeling on a four-leaf clover is because maybe the way that the clover is building its leaves might be following a program that's in the biology, and I wonder if the leaves are often Fibonacci numbers. So this is an interesting question. Like somehow somebody had asked if these Fibonacci numbers, like 1, 1, 2, 3, 5, if these things come up very often in nature. And they do. Actually, if you look at nature, you'll find out that lots and lots of times, like the number of leaves that something has is going to be one of these numbers. And that's again because somehow as you're making any biological object, the instructions to make it need to be very simple. And it's easiest to make instructions that say, like, when I make this thing, then I make, like, the next thing is the sum of the two previous things. So my gut is I would just say, I wonder if it's because 4 is not a Fibonacci number. That would probably be one of these reasons. Of course, there are also four-leaf clovers, but it could be that the majority of the four-leaf clovers are following some instructions which are not actually doing it this way. The instructions might usually be to say, do the whatever you had before, and then whatever you had before that, make another one, and then at that point you stop. Maybe you stop at 3 leaves. But then somehow, maybe when it goes to 4 leaves, it was a mutant of some form. And this idea of like how many leaves things have, and going into nature and looking for Fibonacci numbers, you will notice Fibonacci numbers everywhere. Now, why we like 4-leaf clovers? I think we like 4-leaf clovers just because they're rare. It's like somehow whenever there's something rare, people say, oh, that's kind of neat. And then you feel like you got lucky if you found one. What else do we have here? Oh, okay. Joshua Wu asked a question. And this is like not really a math question, but it's why do people use money? Well, you don't have to use money. We could just deal with a different way instead. What we could say is that everyone is good at something. Oh wait, no. The way I should say it is, there's one option. One option is called no money at all. It's called every person for themselves. You better learn how to farm. You better learn how to hunt. You better learn how to make clothes. You learn everything. And once you know everything, you can go and survive on a desert island. Hopefully they have enough water to drink. But like you can just do everything yourself. Unfortunately, that's highly, highly inefficient. That's called like being, I don't know, that would be called like being a bear or something. I guess bears have to do everything, right? So somehow, like if you had to do everything yourself, it would be very, very inefficient. And what humans have done is we've said, no. Look, this person is going to be very good at making shoes. That person is going to make the iron ring that goes around the earth, and they know what they're doing. And this person over here, this person's really funny. We're just going to watch this person and they're going to make us laugh. And that's going to make us happy. Like we sort of all decide we'll all do different things. But then the problem becomes, wait a second, but how does this person make other people laugh enough to get a share of the food that's being hunted? And so the main point is that somehow you need to have some way of exchanging. Now, of course, you could say, let's not exchange. Let's just all be really, really good citizens. Everyone work as hard as you can, and we'll all share. There's a problem there. People are lazy. So the problem, unfortunately, is that if you tell everyone, hey, everyone just do their thing, and we'll all share at the end. It sounds good, and in fact, it sounds wonderful. That would be the great thing if we could do that. But the reality is, unfortunately, somehow people don't really do that. And if they don't really do that, it's almost like, right now we have all these online classes, and I'm talking about like school being online or college being online. And our big problem is that somehow we tell everyone, hey, we'll give you a test, just do the test. Or we'll give you some homework, just do the homework. Or we say like, hey, come, watch my Zoom, join my Zoom class and just like pay attention in class. And then you go and find out that somebody figured out how to make a video for their Zoom background, which is a video of them paying attention. And then they ran off somewhere else and did something else. Actually, that's possible. But anyway, please do not do this at home. I'm not here to go and give everyone suggestions of what to do at home. Please do not make that fake video of yourself in the Zoom classroom and play it for your teacher. Okay, please don't do that. Right, but in any case, it's like somehow, this is just like the way the world is, right? Somehow people do these sorts of things. And so why I guess we need some money is that we can then say, look, this person actually worked very hard. And since they worked very hard, they are entitled to a little bit more. And I think that's basically what happens. Oh my goodness. Sophie Tang says that this is what someone in the Chinese class does. Oh no. I was hoping you guys didn't know this yet. All right. Anyway, let's keep going. Oh, Carbon News has an interesting question. How do hackers find out our passwords? That's a good question. Let me tell you about how passwords are actually stored. This is interesting. So, you know, when you go and log on to your favorite website, maybe it's YouTube, you have to type in your username and you type in your password. Okay? So there's two things. There's a username, and there's also a password. So now, here's a question. Why do we even need passwords at all? Why don't we just make it so that everyone chooses such weird usernames that nobody can guess what they are? That seems quite reasonable, right? I mean, what if we changed YouTube and we just changed YouTube so you don't get to see other people's usernames, but so that everyone's username is some nonsense like Z, J, Q, X. I guess I just put the letters that are worth a lot in Scrabble, but that's not what I was trying to do. A, E, I, O, U, 76, 1, hi, now we are done. Okay, suppose that was the username. Like, come on, is anyone ever going to guess that username? It's sort of like your password. Maybe your password is like this too. So what I'm trying to say is like, look, maybe we don't need passwords. Let's just do everything with like super long usernames and make it so that nobody else can ever guess your username. Well, here's the problem. This is what you type into YouTube when you log in, suppose. And then what happens is that YouTube needs to know, are you actually that person? So somewhere inside YouTube, on the other side, they have what's called a database. Or you can think of it as they have a big list. And there's a big list of usernames. So somewhere on YouTube's side, deep inside YouTube, YouTube has a huge list. And the huge list, on it, somewhere, it has your username. Z, J, Q, that whole thing. And then YouTube says, aha, there's the person, they exist, and they let them in. Now here's the problem. If anyone ever hacked into YouTube, they would say, oh, look at that. I got all these people's usernames. Now I can go and log in as anyone because all you need is the username. You don't need the password. So that's why you need a password. Does this make sense? So first I'm showing that, you know, if there were no passwords, at first it seems okay. Just make sure no one can remember it. But the problem is if anyone was ever actually hacked their way into YouTube, they would see your whole username written out like that. And then they would just go and say, now I'm going to impersonate you. To be honest, it seems like it's pretty easy to impersonate people judging from this chat of how many Po-Shen Lohs there are. But in any case, if you just wanted to impersonate one particular person's YouTube account, you could just do that. So that's why we have passwords. So now the password, now we don't need to have such a fancy username. Look, the username can be way simpler. The username is now, there's some green dots. I don't like green dots. The username is now something very simple. It's just called Po-Shen Loh. And you know, I have to make some kind of a password, right? So suppose I make some kind of a password. What's a good password? I have a good password. Let's call the password green. Maybe call it green shirt. All right, so that's not actually my real YouTube username and password, by the way. But in any case, like suppose that's what I did, right? Suppose I have this username and this password. Now what do you do? So let's look deep inside YouTube. When you log in, you go type, and you say, okay, here, I'm Po-Shen Loh, and here's my password, green shirt. And YouTube says, why aren't you wearing a green shirt? Well, you guys already say that for me. But anyway, so I've got this thing deep. And then deep inside YouTube, there's a little table. And the little table, very luckily, says, well, there is someone called Po-Shen Loh. And look, right next to that Po-Shen Loh, there's a green shirt. By the way, this is not what happens, but I want to talk through why this is not what happens. Suppose that's what YouTube did. Why aren't you wearing a green shirt? Yes, exactly. So suppose YouTube actually has both my username and password sitting there. Now, if that's the case, actually, if someone hacks into this, they can still impersonate me. They just look at that and they say, oh, look at that. There's a Po-Shen Loh. And there, it says green shirt. Aha, now I know it. I will go to YouTube, type Po-Shen Loh, type green shirt, and suddenly I can post as if I'm Po-Shen Loh. That would be a huge problem. So that's why this is not what YouTube does. Instead, if you look at YouTube, deep inside YouTube, it doesn't have Po-Shen Loh and green shirt. Instead, it has Po-Shen Loh and some horrible nonsense like percent 23 ZG7 exclamation mark. Actually, probably not. Who knows? But like all these random symbols and random stuff. I just made up something random. Okay, it's pretty long. Something pretty long. But for whatever reason, when I type in Po-Shen Loh and green shirt, YouTube says, that's right, you can come in. And this is because they use something called hashing. They actually run a function. So they have something which can, it's called a function, but it's just a way of taking any password you have, like any bunch of letters. So this is actually very standard. It's not only what YouTube does, it's what everyone does. We actually don't need public and private keys for this. This is actually called, for example, one way is called bcrypt. Another way is called SHA-512, right? There are these like secure hashing methods. And these secure hashing methods, all it means is no matter what you have as something here, there's a function that you can compute from that, and you take this thing, whatever was typed in, and you compute, and you compute, and you compute, and compute, and out spits out this. So here's what happens on YouTube. You type these in as you're logging in. YouTube says, hi, Po-Shen Loh, okay, but is your password really correct? It just takes this password, and it does that compute, 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 and it creates, after computing a while, it gets the blah, 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 blah that corresponds to green shirt, and it checks that against this. If they match, then it says, you're through. Now, this is why this works so well. Because suppose the hacker gets this. The hacker still can't log in as me. Because the hacker doesn't know what you type in to then let you compute, compute, compute to get this. Does that make sense? It's a very complicated way to get from some words into some nonsense. But it follows a very specific function. It's a rule that no matter what you type in here, there will be some blah, blah, blah that comes out there. And now the deal is, since it's very hard, near impossible, to reverse this function, if the hacker sees this, they have no idea how to log in as you, because it's not your actual password, right? So the point is, this is actually one of the secrets of cryptography. No, it's not a secret, I mean, now you know too, right? But if you ever build a website, this is why in your database, you should only store plain text usernames, and you should never store a plain text password. You should always take whatever the passwords are and hash them and put it here. Now somebody says, well then how does hacking still exist? Unfortunately, there are some websites where the people making the website forgot to do that. And sometimes in the website, the people who made the website were like, who needs to hash the passwords? Just put the username and password next to each other. Surely that's good enough. And then some hacker comes along and hacks it. And when they hack it, so here's the fundamental difference. If you see this nonsense thing, you have no idea what it came from. On the other hand, you know what happens? If there's one website in the world, one website, where the people who developed it were not very careful, and they just said, yeah, I'll just leave them in plain text. Then the hacker goes into that website, and after they go into that website, they say, oh, Po-Shen Loh's password is green shirt. Aha! Now they can go and hack into my YouTube. And what they also say is, most people use the same password for lots of websites. And then they go and attempt to go to other websites, and they keep trying Po-Shen Loh green shirt. Po-Shen Loh green shirt. And soon they find out that, oh my goodness, his bank account has the same password. His Gmail has the same password. His everything has the same password. It's terrible. Actually, when this happens, when these password hacks are done, people find out that actually the most common passwords are things like 1, 2, 3, 4, 5. I mean, when people hack these things, they find out that unfortunately there are a lot of people in the world whose passwords are like 1, 2, 3, 4, 5 for everything. That's not very good. There's also a very common password. A very common password that people use is actually password. I mean, this is like, this is like somehow we have password 1, 2, 3. So unfortunately, there's a lot of people in the world. By the way, if you're one of these people, please don't do this. I'm also showing you that if you use an easy to guess password, someone might go along and be like, gee, I wonder if Dayit's password is just password, right? So this is why you actually need to use different passwords for every site. By the way, the thing I just showed you shows why you should use a different password for every website. It's because you have no idea whether the people who made that website were lazy. You have no idea if the people who made that website didn't hash the password. So there's a problem. Like, you might have just given them a password that's sitting in a database waiting for somebody else to steal. And the moment someone else finds it, they will go to all of these other websites and attempt to impersonate you, right? So one of these things is like, that is why you shouldn't use the same password for every site, because it's not even up to you. You have no idea if the security people at that website know to hash their passwords. If they don't hash their passwords, you have just gotten your password potentially detectable, and then they could go elsewhere and log in. And also, by the way, if they didn't hash their passwords, they probably also forgot to secure their server in lots of other ways. What that means is they're even more likely to get hacked. Okay, so I hope that is giving you some answers. You see, the reason I talked all the way through this is because this actually sounds, I mean, this is something which, if you're not thinking about it, what I wrote here sounds reasonable. Like, if somebody was a newbie and they said, yeah, I'll make my whole thing this way. I'll just get my usernames and my passwords and I'll make a list. And if they do that, they get hacked. I mean, they make it easier for people to get hacked. So hopefully this is interesting to you guys, because now you know, if you're ever going to go and build a website, to also think about all these other security things. But once you think about it with math, we're basically using logic and game theory. We can figure it out. Next question, more about passwords. If 10,000 of your fans tried to guess your password, statistically speaking, how long would it take to hack into your account? Let's try. So you said 10,000 of the fans. I see. So there might be 10,000 of the fans. We have about 10,000 YouTube subscribers. So the question now is, we're saying, look, we have 10,000 fans. That's 10 to the power of 5 fans. Somehow these fans are trying to impersonate me by hacking into my account, okay? But as I said, it's probably easier to impersonate me just by changing your display name. But anyway, 10,000, wait, no, that's not 10,000. I can't even do math anymore. It's 10 to the power of 4, right? 10 to the power of 4. Thanks, everybody. Okay, so suppose you have 10 to the power of 4 fans, okay? Now, if we have 10 to the power of 4 fans, how long would it take to guess the password? Well, how long is my password? I mean, I'm trying to remember. I don't know off the top of my head how long my password is, but I'm going to say my password is probably around, probably around 12 characters, okay? So password length 12. Now, my password is not just hello. My password is not just password. It's not even just like some normal English words. It's some junk. So in that case, if you actually wanted to guess it, you know, the number of different things you need to try for every one of those positions, it's like password length 12. And, you know, in each position of the password, I shouldn't have said 12. I can't even count. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay? For each one of these things, how many choices do I have? Well, I have lowercase letters, A to Z. I have uppercase letters, capital A to capital Z. I have digits, 0 to 9. I've got like random weird symbols like exclamation point, minus, backslash, you know what I mean? Like weird symbols, and also weird symbols. So if I have all of this, how many choices do I actually have to put something there? Well, I have 26 choices for that one, 26 choices for that one. That's 52 already. 62 from here. Add some more. How many weird symbols are there in the world? Let's just say there's probably about here's what I'm going to do. I'm going to say, just for ease of calculation, let's say there are 70 symbols. 70 options per place. Now, do you know why I chose 70? There's a reason I chose 70. The reason I chose 70 is because it's going to be nice to multiply soon. So if I have this 70, right, now I've got 70 to the power 12, and I'm trying to compare that, right? So that's kind of big. The number of passwords is 70 to the power 12. What's 70 to the power 12? The way I'm going to do this is I chose 70 on purpose because 7 times 7 is 49, which is about half of 100. So this is going to be about, I'll call it 5,000 to the 6. What I just did here is I said 70 squared is 4,900, which is about 5,000. And I was actually choosing this on purpose because 7 squared is 49, which is around close to 50. And 5s are nice because they're close to halves. It's very, very, very convenient. So I'm going to say that this is 10,000 to the 6 over 2 to the 6. Do you see what I did here? What I did here is that 10,000 divided by 2 is 5,000. And this is going to make my multiplication a lot easier, right? So now I'm going to say, how long are you going to take to do this whole process? Well, you need to go and have, like all of these people, how many passwords does each person have to check? Well, there's 10 to the power 4 people, so they get to share all this work. Actually, 10 to the power 4, I'm going to call that 10,000 because I have a 10,000 in the numerator. So in that case, the amount of work each person has to do is each person only has to check this number divided by 10,000 many passwords. How much work is that? Each person, each fan, checks 10,000 to the power 5 divided by 2 to the power 6, which is 64 passwords. This seems like it might take a long time. Oh, there's a 32, you're saying. There is a 32. So where's the 32? I'm not sure if there was a 30. Maybe I did something wrong? It could be that I did something wrong. If I did something wrong, please let me know. So we keep going. And so this 10,000 to the power 5. Oh, you're saying there are actually 92 possible characters. Oh, really? Oh, if you're limited to keyboard characters, temp ID, you're great. You make my life even easier. I would call it 100 then, and it would be even easier to do. I was actually trying to do this 70 on purpose, though, because I wanted to show how close 7 was when you square it to things that have to do with 2. And actually, 0.707 happens to be the square root of 1/2. That's actually why I chose this, because there's also some nice math inside here. But if I do this, approximately where am I? So that's about 10 to the power 20, because there are 4 zeros after the 10 after the 1 for 10,000, and so I have about 10 to the power 20 divided by 64. 64, I'm going to say, is like, I don't know. Let's divide it by, let's divide it by 64, which let's call it dividing it by 50. That's going to be easier. So that's going to be 10 to the power 18. I'll pull out a 100, and it's 2 times 10 to the power 18. So basically, I took a 2 because 10 to the power 2 is 100. 100 divided by 50 is 2, so that's very nice. So now each fan has to do 2 times 10 to the power 18 passwords to check. That will be a very, very long time. So I think it probably won't happen for quite a while. And that's actually why you should not choose passwords that are too short. Once you have passwords of length about 12, which are really, really random looking, it can be very, very hard to guess your password. Which is why, if somebody wants to guess your password, the easier way is if you use the same password on another site and someone hacks the site. Actually, now that I've told you this is also showing if you use a website that looks kind of shady. If you use a website that looks like, shady means not that they're trying to do anything wrong, but it looks like they're kind of like not super professional, they're kind of new, the user interface looks kind of weird, it doesn't look very polished. If you use one of those websites, you might want to be a bit careful to choose a very, very different password than you ever have used, in case they didn't only not know how to design a website, they also didn't know what to store on their server inside it. Okay, what else can we do? Oh, wow. Now we're talking about passwords. How do you remember your passwords for every site? Asks Andrew Zhao. So there are a couple of ways to do this. One way is to use something called LastPass. I saw somebody is using LastPass. This would be if you trust the people at LastPass. I'm not sure I do. Sorry, there's nothing wrong with the people at LastPass, but it's like you could use some website that says, trust us, give us all your passwords. We promise we won't tell anyone. Hopefully. Okay. So, what I actually do is I use my own passwords. I have my own password file. I actually made my own LastPass. Right? Like, so the principle of LastPass is you need to have a password file that it's actually not possible for someone just to read it. So I in fact use something called encryption. This is this number theory stuff that has to do with what people commented about private key, public key encryption. So I actually have an encrypted file where I know one password, and when I use that one password, I'm able to go into the file, do stuff with the file, and close the file again. That's one way I do things. Another way I do things is for some other passwords, if the passwords are just numbers, like there are some things in life where the passwords are numbers. Actually, I came up with a system which based on what organization I was making the password for, I had my own function that could compute as a function of that organization name, it would spit out a number. And so all I had to do, I could have a different password for every single organization because I just had to know one function, which is called, if I see this spelled out name of that organization, I just calculate the function myself and I'm good. And by the way, since John Conway was brought up earlier in this, I can tell you John Conway had a very interesting way of doing his passwords at Princeton. So I was a PhD student. I was a PhD student when in Princeton, a few years ago. Well, more like 12 years ago, not that few anymore. But back then, I would actually see him all the time in the common room because I really enjoyed working in the big open room with lots and lots of windows and interesting mathematicians always walking around. So I saw him all the time there. And now, it was well known that John Conway's way of logging into his computer, if you went to a computer, the computer would basically ask John Conway, what day of the week was January 12th, 1622? And John Conway would, bam, figure it out and type it in. And John Conway was just faster than everyone else at figuring out what day of the week it was. So now, of course, I don't think he does that anymore, in the sense that now we have mobile phones. But there was a time when people didn't have mobile phones everywhere. They couldn't just pull out their phone. And if you wanted to log into a computer, it's like, you wouldn't be fast enough at trying to figure out what day of the week it was, right? So in any case, I mean, this is just an interesting concept that somehow you could compute your password instead. And so the thought is that somehow if you can find a way to compute your password, then you have a way of having a different password for every different site. Okay, what else can we have? It looks like we're down to basically the last question here. Oh wow, this is interesting. Eric Feng asks, would you rather teach in person or by computer? Well, these are complicated. So I really enjoy teaching in person because I like to see the responses on people's faces. I love going to different places. I also found out that if you go to a city, you're more likely to get people coming from all over the city because they're like, oh, we can actually see this person and we can see in person, and it has a nice draw. So I do enjoy that. I hope we can do that again soon. On the other hand, during this whole crisis, I've learned how to also teach by computer. This particular YouTube live session seems to work quite well, in the sense that I can even see what everyone else is talking about, and we can even have this kind of a conversation with the chat. I think that's really interesting, by the way, because I didn't know beforehand that it would be possible to sort of have this kind of a discussion remotely. Now, I also think a lot, though, about what kind of impact I can have with the times that I put out. That's one reason why I always tell people, please try to tell more people to join this, right? Because the time that we spend is valuable. All the things that we're choosing to do with our time, we could do other things too. And some of the other things can also help a lot of people. And so whenever I look at the impact that one does in person versus online, actually online, we're doing quite reasonably. We have like 232 people right now. And the fact that we are able to every single day reach over 200 people, that's actually not bad. Although, again, as I'm thinking about these things of like in-person versus online, to me, if we can push that number into the thousands, that would be very, very clear that somehow doing this thing online is very, very effective at reaching lots of people. So that's where I'm going to say, do I like teaching online? Well, in some sense, if we can keep getting more people coming, that would be great. And especially now that many of you know what this is about, if you tell other people what this is about, quite possibly you'll also get more people in. And then I guess there's the last part, which is what does it mean to be even teaching online? This is a live broadcast. To me, I also don't really know if this is really considered teaching, in the sense that I'm not teaching you any particular skill. And the reason is because those we actually put in our not live online courses. So if you ask me, I actually feel that filming all of those is also something I was very proud of doing, because by doing that, it became possible for not only a few hundred people to see each video, but thousands of people. So actually, my goal is that eventually those videos that we actually make, which are part of the official online course, our hope is that actually reaches hundreds of thousands, if not millions of people. At which point, then the work that we did is definitely worth it. So the answer to your question is, I love people, so I love the in-person interaction, so that's really fun. The online live chat we're having today is somewhat of an approximation to it. I'm glad it's working. It will work better if we have more people. And ultimately, I thought it was worth it to go and invest basically 6 to 12 months really filming out some of what I feel are the best ways to explain math, because then those are lasting. Those don't need to worry about whether or not somebody is watching this particular session right now. Those will last for generations for anyone who wants to learn math in that creative way. So answer is, I like all of them, and I will ultimately choose what to do based on what has the most impact. Well, that being said, I unfortunately have to go. I have to continue on with our Novid work. I'm actually in the middle of doing some research on our actual way of building the app. So I'll be going right back to writing some Java. But I hope that all of you have a good day, and I'll see you all tomorrow. Thanks for joining.